Very good morning to all of you.
Good morning, sir.
At the outset, I would like to thank organizer of this workshop for giving me this opportunity to talk about how to estimate SOC. Hope you are all aware about the SOC. As you know, battery we already are using it for low power applications. In battery, how do we store the energy? Are you aware? Simple high school chemistry. You know about redox reactions. When I say redox reactions, we are talking about simultaneous oxidation reduction reactions. Battery also there are going to be two different type of battery: primary battery and secondary battery. Primary battery, we use a dry cell. You should throw actually. It cannot be recharged actually. The battery pack what you use in electric vehicle, we need to do charging also. Rechargeable battery we call secondary battery and so on. Before coming to battery pack, let us just discuss different type of electric vehicle. To begin with, you can see here what you have in conventional vehicle as compared to electric vehicle. Electric vehicle, what are the different subsystems you have? I consider electric vehicle as a subsystem. You just see from this picture what are the different components you have in electric vehicle as compared to conventional vehicle. We talk about powertrain, isn't it? Battery management system is nothing but, to put it in layman term, your power electronic circuits, which it takes care of continuously monitoring health of the battery pack. When it is being charged or discharged, or to what mode it has to be discharged, you know about constant current, constant voltage, the different modes by which you discharge the battery, likewise the different mode by which you charge the battery. Battery management system takes care of health of the battery. So the BMS is acting as interface between your battery pack and rest of the powertrain. When I say powertrain, we have battery pack, BMS, along with it, battery produces what type of power? It put DC power. DC power needs to be converted into AC power using inverter. Okay, that's where we have a converter inverter. Inverter converts from which power to which power? We are all electrical. DC to AC. And again, in the electric vehicle also we have a lot of auxiliary system. We have infotainment, lighting. For that, what you need to do? I cannot use the DC power directly. I have to convert DC to DC. We require converter. That means we have battery pack, BMS, along with it we have inverter converter. Then it comes motor actually. So what you need to ensure for the vehicle to move on the road? We require power coming from the motor. Motor should be able to deliver record torque and speed to the wheel. It's clear? Powertrain constitutes energy source, BMS, converter, inverter, and motor. Along with it, you have controller also, which will be able to sense continuously what power is required for the vehicle to move on the road. Slow speed, high speed. In powertrain, along with what I said about motor, the motor also acts as generator. You move on the road, you go on the slope, you heard about regenerative braking. When you move on the road, continuously battery is getting drained out. When you move on the slope, we exploit, when you apply the brake, when you go on the slope, we can convert wheel movement, kinetic energy into electric energy. That we use motor as generator actually. Through regenerative braking, possible to charge the battery also. Is it clear what I'm saying? When I say powertrain, you should know about what are the components in the electric vehicle. Energy source, BMS, converter, inverter, motor, along with the controllers, hardware actually. So BMS, what does it take care? BMS, it has got sensor, current sensor, voltage sensor, temperature sensor. When the battery is being discharged, I know what is the typical temperature rise of the battery. Now we talk about battery needs to be charged quickly in 5 minutes, 10 minutes actually. But the way the battery pack has been designed, accounting from mechanical perspective, electrical perspective, cooling, I call thermal management of the battery pack. All these aspects need to be accounted. Alongside, we need to know what cell chemistry you have chosen to design the whole battery pack actually. So comparing it with IC vehicle, what is that you don't have an electric vehicle? When I say IC, we say internal combustion engine actually. You don't have the engine. Do you have the gearbox here? Do you have the gearbox, the electric vehicle?
No, sir.
Just compare your conventional vehicle with electric vehicle actually. Electric vehicle, you don't have the engine. The power source, basically battery pack. Motor is taking care to deliver the record torque and speed to the vehicle to move on the road actually. And again, to compare a conventional vehicle with electric vehicle, what is the key advantage you have? The electric vehicle is almost maintenance free. Even though at the beginning it could be expensive, the long run, if you see, it's almost it's offsetting the cost when you compare with the conventional vehicle actually. Highly energy efficient, 70 to 80% energy efficient actually. You can just see the first 15 minutes. I will just give the key features of electric vehicle, different type of battery. Before I move to how do you simulate the SOC of the battery pack actually. So among several features, which one you will do? I mean, if you compare conventional vehicle with the electric vehicle, which will the feature you will give high importance actually? Yes, more energy efficient and maintenance free, almost maintenance free actually. Why it is 80% efficient? Anyone knows? Yeah. Wear and tear is not there. A lot of moving parts, unlike in conventional vehicle gearbox. Conventional vehicle gearbox, no, it undergoes wear and tear. It consumes a lot of energy, lot of heat dissipation, friction heat dissipation. Such things are not there in battery pack actually. That's where we say when you do thermodynamic analysis, what is the input goes into it, what is the output you get. We can do thermodynamic analysis for energy balance, mass balance, how much input you are giving. We can come out to say that it is almost 80% energy efficient compared to conventional vehicle. Okay. And again, different type of electric vehicle. What is the first one? A request to interact. We have battery operated electric vehicle, plug-in hybrid electric vehicle, hybrid electric vehicle. The last one is fuel cell operated electric vehicle actually. So what is the difference between your plug-in hybrid electric vehicle and just hybrid electric vehicle from the diagram? Before I come to battery pack, I just want to go through electric vehicle. What advantage you have? Key point for the electric vehicle, 80% energy efficient. Almost maintenance free. Two key points you have to remember. Then we want to look at variety of electric vehicle. Why I have to look at this slide? Now already we have a car. I don't want to buy purely battery of electric vehicle. Is it possible to retrofit battery pack into the vehicle what you already have? It's possible. So what is the role of hybrid electric vehicles? If you look at this picture, what do you have in hybrid electric vehicles?
Along with IC engine.
Purpose of showing this slide, I already have the vehicle. Why should I go for buying electric vehicle? I will go for hybrid. I can retrofit battery pack into the vehicle what already you have. That we call hybrid electric vehicle. You can have both engine plus battery pack also. Okay. And hybrid electric vehicle itself, you have plug-in. What is the difference you have here? Compare these two.
Charging of the battery.
Charging, isn't it? And we have fuel cell operated electric vehicle also. So what is fuel cell by the way? Fuel cell also is a special type of battery wherein the fuel we continuously supply from external source. Organic hydrocarbon plus air when they get mixed up. When it's a hydrocarbon, they undergo decomposition. We need to have source hydrogen plus oxygen. We continuously supply this fuel, hydrogen and oxygen. They undergo redox reactions at the respective fuel cell, wherein we have both anode and cathode. When they undergo redox reaction, what is the output you get in fuel cell? Output from the fuel cell when they undergo redox reaction. Hydrogen when they combine with the oxygen, what does it produce? Water plus energy actually. There are fuel cell operated buses, heavy vehicle. Even we can do analysis, cost benefit analysis. If you go for fuel cell as compared to battery operated electric vehicle, fuel cell it has its own USP, unique selling point for the fuel cell. For heavy vehicle, we can go for using fuel cell also. But lithium ion now cells they are cheaply available actually. 5-6 years ago it was expensive. Now almost for throwaway price you can get lithium ion cells. You know about OCD? Each lithium ion cell chemistry it has got its own OCD. What is OCD by the way? You already know. When you develop new cell, okay, you have to establish a cell chemistry. Of course, you know what is the output voltage it can give. For that, you should know open circuit voltage. It should be almost close to theoretical voltage. From electrochemical principles, for a given cathode and anode material, I already know what is the voltage it can give actually. Open circuit voltage. Being not connected to the external load, each cell, what is the EMF it can produce actually. That we say open circuit potential. This OCD value is very much required when the battery is being used continuously over the longer period of time. Each time you want to know at what rate cells are undergoing degradation, the simple measurement by using multimeter, you know what is this voltage it gives actually. Aged battery, OCD value will not same like what it was at the early stage when you purchased the cell actually. So OCD is very important. OCV value needs to be continuously monitored as the battery undergoes aging. The OCV can be connected to finally SOC, the state of charge for the cell actually. And again, this particular slide to compare, we have this battery of electric vehicle, hybrid electric vehicle, plug-in hybrid electric vehicle, and the last one fuel cell. What is that we need to compare? This slide, in fact, I already given this whole handout also. You should be aware. Each vehicle, you look at what is the energy source they use. We have this, what is the propulsion, what is the energy storage. You just go through this. What is the difference between here your top one battery of electric vehicle compare with plug-in hybrid electric vehicle in terms of propulsion and energy source actually. And then we have here typical features, okay, and then efficiency you compare. Finally, typical comments with respect to cost. Yes, all the time we talk about cost actually. Comparing among different type of battery operated electric vehicle, you see the typical efficiency and their comments and who are using it already. The last column it shows actually. Manufacturer. Okay. Each battery is used by what type of vehicle and the last one actually. Can you just go through this and tell me which one you will opt for? Leave alone your ICE or fuel cell. Which one you will operate? Looking at efficiency, you can see here. Who is using predominantly what type of electric vehicles? This is very useful. I mean, look at the energy source and propulsion. Which one you will opt for? Yeah, which one you will opt for? Hybrid or plug-in hybrid electric vehicles? Yeah. Which one you'll go for? Is it? I'm just asking, putting this slide, whether you'll go for completely battery operated electric vehicle or hybrid electric vehicles. I've given all the features and the model also at the last actually. Who is using what? What type of? Tata, Tesla, all such things actually. Which one you'll go for? You will go for battery operated or hybrid electric vehicles. If you're already having the vehicle, you can go for hybrid. I don't want to go for new vehicle. I just want to retrofit battery pack into the already vehicle what I have. Otherwise, it's better to go for completely battery operated electric vehicle in the long run. It's going to be almost maintenance free, looking at the efficiency and so on. Okay. And I'll need to show that who is using what. See, ultimately, you can discuss everything. Finally, who is the user? The purpose of showing this slide, ultimately, who is using what type of battery pack they use actually. Is it purely hybrid electric battery or plug-in hybrid electric vehicle? What type of battery pack they choose? I should know who is using. That's what this is. Sorry. And again, batteries also. Just so you know, I already mentioned about. We have primary battery and secondary battery. Okay, let us just discuss about cell level. What do you mean by cell? I already mentioned about primary battery, secondary battery. Primary battery is not rechargeable. You should throw. Rechargeable battery is the one we are using it for electric vehicle. This we call secondary battery or rechargeable battery. The cell level, what do you have? You have anode, cathode, and electrolyte, isn't it? And the cell, when you try to connect them, series parallel configuration, depending upon what is the capacity you want, it may be series parallel series configuration. Okay, cell you try to assemble them. How do you connect cell to cell? Fundamental level cell, several cells being arranged in parallel series, they tend to become module. To interconnect cell to cell, we need to have the bus bar. What is the role of bus bar? What is the role of bus bar? We are interconnecting the cell. I want to have 1 kilowatt, 10 kilowatt power from the battery. Single cell can it deliver? Cell needs to be assembled. When you assemble them, please listen carefully. Cell is already developed by chemistry people. They establish OCB value for the single cell. Single cell will have anode, cathode, electrolyte and put it in the compartment container actually. I need to ensure electrical performance of the single cell, having anode, cathode and electrolyte, having chosen appropriate material for anode and cathode. When you connect the cell to the external load, I should know how much EMF it can generate under no load condition. Okay, how much time it can continuously deliver the power to the external load. So you should know OCB value for a single cell. When you connect them in series or parallel configuration, what for your assembling cell? A single cell cannot give. I'm just discussing more fundamental level. Why I should make model. Several cells being connected in series parallel. I want to achieve record capacity from the To begin with, model, cell, and then model level and the pack level. Several models, when they're interconnected, they become a pack. Look at two-wheeler or the three-wheeler or four-wheeler, we have the battery pack. The internal cross-section of the battery pack, if you look at it, there are thousands of cells, they are being arranged in a series parallel configuration. Again, coming to when you fabricate a model, cell, when you assemble them, you are making model. What is required? Expertise. I need to be good at electrical. I talked about bus bar. Series parallel configuration or parallel series configuration. You need to design the bus bar with respect to electrical. When I say electrical, you talk about contact resistance. How do you connect a cell to cell through bus bar? I have to come to fabrication of joining. We use welding. Ultrasonic spot welding we use. The moment you try to join cell to cell by using bus bar, you are using some welding operation. So the welding operation, if you don't take care of appropriate process parameter correspond to welding, you are going to damage the cell as well as it is going to affect contact resistance of the cell being connected to each other actually. If the contact resistance becomes very high, what will happen to the cell output voltage? The bus bar needs to be designed for a mechanical perspective and electrical perspective. You know what type of bus bar we use? Nickel coated copper. Nickel coated copper is used as a bus bar to connect cell to cell. When you design the bus bar, I need to account for its strength from mechanical perspective as well as its electrical conductivity. Above all, the kind of joining process used to connect cell to cell. If you don't take care of proper joining from cell to cell, sometimes your bus bar will delaminate. When you use the battery continuously, you cannot escape I square R loss. Ohmic drop. Heat dissipation will be there. Due to heat dissipation, your bus bar it may simply delaminate actually. Bus bar may come out if you don't join properly. What will happen to the bus bar if it comes out? They will short circuit. Because of short circuit, what will happen? We talk about batteries catching fire. You often heard about thermal runaway or leakage from the battery pack due to water attrition. Due to water attrition, if you don't take care of proper design codes with respect to electrical, with respect to mechanical design, with respect to overall, if you talk about big battery pack, if you have not taken care, properly positioning the cell, you need to have a spacing. They should not touch with respect to each other. The way they are positioned, the way they are being connected through joining process, if you don't, that's what I call mechanical design. Electrical design, I need to take care of with respect to joining process, how much contact resistance is going to induce actually. If you don't take care of that electrical design perspective for designing the bus bar, that's where it leads to short circuiting, and again it boils down to I square R loss. Bus bar will delaminate. That could be short circuit. Because of that, you tend to see a lot of heat dissipation. For all such things, the BMS takes care. It continuously senses current, temperature, voltage. It continuously senses any untoward incident. BMS will take care actually. Safety. Safety is taken care by the BMS. And again, battery also, it should not be discharged to zero voltage. We call depth of discharge. Battery pack should not be discharged to 100%. We call DOD, depth of discharge. Much before that, for safety reasons, we stop actually. Like that, we can never do overcharging or over discharging also. All such things are taken care through BMS actually, battery management systems. So I just to introduce the terminology, what I mean by cell, fundamentally we look about anode, cathode and electrolyte. And when I talk about anode and cathode, at the cell level also, what property, say I am designing at the electrode level. You look at lead acid battery, what you use in the conventional vehicle. What for we use? The lead acid battery, the conventional vehicle. You can see the rectangular box. If you look through cross section of the lead acid battery, what use the conventional vehicle. What for it is used? Even the cell level also, I should be good knowing about the electrical properties. Anode, what material I am choosing. Okay, anode material, electrical properties. Cathode material, electrical properties. Okay, not only knowing their typical mechanical strength of the anode and cathode, I should know what is the conductivity. When I say about conductivity, what I mean for anode and cathode material. You know about the electrical conductivity and ionic conductivity. Okay, you take for example lithium-ion battery. We use cathode materials. In cathode material, we use the transmetal-based oxide. Material property in terms of electrical conductivity should be known. Ionic conductivity should be known. What will happen to ionic conductivity with respect to temperature? Lithium ions are moving back and forth. Since lithium ions are able to move at very high speed, That's why we talk about energy density, power density is very high for lithium-ion battery. It has very good electrical properties. Being lightest, okay, we can ensure high power density, energy density for lithium-ion battery compared to all other type of battery, what you are aware actually. So even at the cell level to design also, what material to be chosen? Lithium-ion battery, already we are using it. If you ask me what is new things are going on, the chemistry people, they continuously work to develop new cathode material and anode material. Cathode materials are transition metal oxide. You know about transition metals, iron, cobalt, nickel. No? They all come under transition metals actually. So transition metal oxides are used as cathode material. For anode, right now, if you look at lithium-ion battery, we use graphite is used as anode material. Now people are slowly moving towards better material, silicon. They use silicon, other type of anode materials. But slowly they will come into market. Again, looking at cathode and anode, how much power density I can expect if I replace the existing metal with the new materials. So there is continuous development for cathode material and anode materials also. So I just covered here what is cell I mean modular pack level. Yeah. And again charging also. We are impatient. I want to charge the battery. I just want to introduce level 1 charger, level 2 charger, level 3 charger. Which one you'll go for actually? I just want to introduce different type of battery, different type of electric vehicles. Level 1 charger, level 2 charger. Which level charger you will choose? Among three, which one is faster? Yeah. Which one you will choose? Level 3. Quick charging, what will happen to the battery? Repeatedly, I want to highlight, if you want to design and develop battery pack, having chosen appropriate cell chemistry, time and again, design, accounting for electrical perspective, mechanical perspective, above all cooling perspective. Can I use the same design what was used for level 1 charger for level 3? Level 3 charger, quick charging. It means the way the battery pack has been designed. If you don't account for appropriate positioning of the cell, if you don't account for the proper design of the bus bar with respect to electrical perspective, if you don't account for due to quick charging, I square R loss is going to be very high. Okay, you have to provide instantaneous cooling. I cannot see that battery pack temperature is raising beyond 50 degrees actually. That means you have to provide appropriate cooling solution. It is not one size fit for all. If it is quick charging of the battery pack, I have to look at the technical specification of the battery pack. Can it afford to go for quick charging or not? Very often, we are impatient. Any ITI diploma person just buying the cell, assembling it, putting it into vehicle, that's where we see all the problems. Again, I would like to repeat, if you have accounted proper design code from electrical, mechanical and thermal cooling solution, the battery of electric vehicle is as safe as, is better than conventional electric vehicle, conventional IC operated vehicle actually. Let me repeat, if you take care of proper design code for developing battery pack, it is as safe as currently used vehicle actually. All the thermal runaway leakage problem because of you don't follow proper design code. Now we cannot just like the develop battery pack put into vehicle. We have to go through certifications. You know, ARI, Pune, Automotive Research Institute, there we have to get certified your battery pack. If you want to get into making battery pack, you want to sell it in the market, you cannot sell it just like that. You have to get certification. You have to go for rigorous testing. That's where in future you don't need to be afraid whether to go for electric vehicle or not. It is going to be safe. Okay. So level 3 charger, of course in India we say charging infrastructure is not that good. It's picking up slowly actually. In fact, there is a proposal. Yesterday there was a workshop at the institute. They were saying that if you go on the highway, there are a lot of ATMs are there. ATMs, you can go and withdraw money. ATM, you have the power supply. They want to have a charging solution in the ATM, near the ATM. A lot of ATM, different banks are there. And bank will give incentives. If you charge the battery in our ATM, and you will have 5% discount, 10% discount, and so on. That means that charging infrastructure is going to improve with the time. 5 years down the line, you can see there are several charging stations when you go on the high road. Like you have already a petrol station. There's going to be charging solution also with the time actually. Yeah. Again, you see different type of cells. What are different type of cells you have? We have cylindrical cell, prismatic cell, pole cell. You know, in two-wheeler, what type of cell we use extensively? We use cylindrical cell actually. And again, we refer typical dimension for the cell, 21,700, looking at the length and height actually. Okay. So how do you decide which cell to go? Cylindrical cell or prismatic cell or pole cell? Again, for each cell, looking at the dimension, how much material I can put into cell internally actually. Each cell configuration is unique actually. At what rate reaction they can undergo back and forth. Being cylindrical, prismatic, apart from knowing material property, apart from knowing where it should be positioned, the design geometrical factor of each cell needs to be accounted, how it is going to influence the electrical performance, even other thermal performance, even their mechanical strength and so on. Okay, so we need to know what design to choose for given applications actually. Each application will be unique. Accordingly, you have to decide what cell chemistry you should use, what cell design you have to choose. All such things need to be accounted. We have variety of configuration. Prismatic cell, you can look at the different configurations. Cylindrical cell, prismatic cell, pulse cell, and again you can see typical lithium and their typical high voltage lithium and cell battery. They are extensively used. Okay, again you see lithium and batteries. Just to show you, different parts of the lithium and battery, what electrode we use in terms of anode and cathode, electrolyte. Okay. And again, look at here current collectors. You know, current collector. What is a current collector? I talked about anode, cathode, electrolyte, compartment. Along with the anode, we have current collector. What do you have for typical anode and cathode as a current collector? At the cathode, we have aluminum current collector. Okay, and anode, we have copper current collector. Now, people are moving towards anode-free lithium-ion batteries. Simply, they are using copper alone as a current collector. When the reaction undergoes back and forth, again, time and again, what you are altering, what you are playing with it. I want to achieve always high power density, energy density, battery pack size I want to reduce. When I say anode-free lithium-ion battery, you don't require to use graphite. Just use copper as a current collector. When the lithium, when they undergo back and forth reaction, at the anode location being copper current collector, their lithium will get deposited actually. By removing the anode, you are able to take care of all the properties in theoretical performance. Anode-free lithium-ion batteries. You don't need to use graphite at all. Just use copper current collector. A lot of people with the power plants background, AAA background actually. Any questions you have? I just mentioned about lithium-ion batteries, what anode and cathode we use. Now slowly I will move towards how do you estimate the SOC. Any questions please so far? Even from our faculty side and our student side? You're all with me, no? You're able to follow what I'm discussing. Yeah. Yeah. So typically, the working principle for lithium-ion batteries. What do you have here? I mentioned about anode and cathode. What happens during? In fact, I already mentioned that right now we are using graphite. Now, what is graphite by the way? We talk about graphite and diamond for carbon. What are the graphite and diamond? What do you call? Is it carbon, no? What do you say graphite and diamond? What is diamond and graphite? And about allotropy? How diamond is different from graphite? Why did you use diamond? I am using graphite. I already mentioned allotropy. What is allotropy? Carbon form. What is allotropy? You are aware? The difference between graphite and diamond. Diamond is expensive, we say precious, but graphite is not so. What is the difference, graphite and diamond? Anyone? Graphite and diamond. Both are carbon only, na? Chemical composition is carbon only. But how do you differentiate graphite and diamond? What do you say allotropy? With respect to crystal structure, atomically how they are being arranged. Graphite is basically hexagonal unit cell actually. How the atoms are arranged actually. Okay, with respect to the way the atoms are being arranged to form crystal, the fundamental building block for any solid, we call that as a unit cell. Spatially, how they are positioned, how they are connected to each other. Okay, that's where they differ. We say with respect to crystal structure. When I say crystal structure, atomically where they are located actually. Diamond has different crystal structure compared to graphite. So graphite right now we are using it essentially as an anode, and cathode we are using variety of transition metal oxide. Lithium, nickel, cobalt oxide, lithium, nickel, manganese oxide. We use variety of transition metals actually. These oxides being used as cathode, it has got channel. Okay, wherein the lithium ion can go, that process we call technically intercalation. It is like lithium can get inserted into the kind of crystal structure what is here for cathode. I am referring to, I mentioned about lithium ions are able to move back and forth during charging and discharging. Lithium ions are the one which contributes for taking the energy from the charged battery. Likewise, when you charge the battery, lithium ions are able to move back and forth. They are able to store as well as they are able to get the power from the battery actually. We need to look at what happens during charging and discharging actually. So during charging, I'm just referring to during charging, okay, lithium will move from cathode to anode. Please remember why I should bother about movement of lithium ion. I talk about quick charging, quick discharge, at what rate I can tap the power from the battery. I need to look at internally how the ions are moving back and forth. That's where I talked about transport properties. We talk about ionic conductivity, electronic conductivity. I mentioned about electronic conductivities for lithium is very high. Above all, being lightest, lithium ion can move very fast. When I talk about quick charging, I need to come to lithium ion being lightest. It can go to very high speed compared to any other batteries actually. Compare alkaline battery, nickel cadmium battery, metal hydride battery. Their atomic rate is quite high. They have bigger mass. Being lighter mass lithium ion, they can move very fast. They can carry the charge. It has got very high oxidation potential, reduction potential. All the property being exploited to say that lithium ion battery can deliver much higher power density, energy density, fundamentally dictated by how the ion can move back and forth. I just mentioned before. During charging, lithium ion will move from cathode to anode. Exactly reverse when you do discharging. When you do charging and discharging, anode and cathode, they undergo simultaneous oxidation reduction. During discharge, anode will undergo oxidation. Just remember, during discharge, anode will undergo oxidation. Exactly reverse when you do discharge actually. During discharge, anode is acting as oxidation. During charging, exactly reverse actually. So what I'm talking about, are you able to get? We are just storing the energy in the battery, being connected to the external load. During charging, we want to look at where from this lithium is moving. During charging, from cathode, lithium is moving to the anode. Exactly reverse. So during charging, discharging, how the ions are moving, you should be able to understand. To know that for a cell, what is the OCB value you will get being connected to the external load. This we call closed circuit. Having developed a cell, is a already constructed cell, anode, cathode, and in between what do you have? What I should account for? We have the electrolyte, we have this anode and cathode. Okay, in between what do you have? Can I have, what is this intermediate? I didn't mention about it. What is it here? Anode compartment, cathode compartment. If I isolate the cell, anode compartment, cathode compartment, we call half cell. In between what do you have? Are you able to get? What did you have? What is that? Please. We have separator. Anode compartment should be insulated from cathode compartment. They will get intermixed actually. We have intermediate channel. This is called polymeric separator. It acts as a channel to flow the ion back and forth. Through the channel, the lithium ion can move back and forth actually. And whatever yellow circle you see, what is that? You assume your material anode and cathode. I mentioned about transmetal oxide. They have got a gap channel wherein the lithium ion can come get inserted. That process called intercalation. Okay, it gets inserted, it gets removed actually. So lithium ions are able to move back and forth freely. The moment it goes with respect to electrode, it can get into the gap channel actually. So crystal structure has got void wherein lithium ion can go and sit actually. During charging and discharging, we need to allow lithium ion to move back and forth. Lithium ion to go and stay there actually. The anode and cathode, depending on where they undergo charging and discharging. The yellow circle refers to we have the gap channel where lithium ion can go. That means crystal structure enables lithium ion can come and sit, it can go, depending upon whether they are being charged or discharged actually. Fundamentally, I am trying to explain simple high school electrochemistry. We are exploiting cathode and anode, what type of reaction they undergo during charging and discharging. When the lithium ion, when they undergo simultaneous oxidation reduction, we talk about batteries getting stored energy and then we are draining out the battery when it is becoming to the load. Okay, I am just referring to fundamental. Ultimately, why should I bother about this movement of the ion? If you ask me, why should I care about transfer property? Fundamentally connected to how fast I can do charging, how fast I can discharge the battery. Fundamentally connected to
the movement of ions back and forth, what speed they can move, what charge it carries. I'm going to discuss. When you want to model mathematically state of charge for the battery, you should know what properties are required, what design I have to use. Fundamentally, it boils down to understanding, knowing the properties of this material, as well as what speed they can move. They will dictate what is your SOC of the battery is going to be. That's what I'm just building up the basics for lithium-ion cell, how the reaction can occur back and forth. This middle region is basically isolating anode compartment with cathode compartment. It's only insulating polymeric separator. It's only acting as a channel. Even for this polymeric insulator also, let us say, I mentioned about insulating. Okay. If it starts conducting, what will happen? I want to insulate anode from cathode. Middle region I have separator, polymeric insulator. They should not be conducting. If it becomes conducting, what will happen? The separator also has to be designed. What is thickness? At what rate ion can move through the channel? Polymeric separator also need to be designed according for the electrical properties, mechanical properties, and so on. What will happen if the separator becomes conducting? I'm just asking. It should act as insulator. If it becomes conducting, what does it mean? Anyone? Polymeric separator, it insulates anode compartment, cathode compartment. The moment separator becomes conducting, electrically conducting, what will happen? Short circuit actually. That means separator also need to be designed. How insulating they are. Their dielectric properties should be known. What thickness I have to choose. What kind of channels I have for the lithium to go back and forth actually. Okay, I'm just talking about designing the anode material, cathode material. I mentioned about different type of design for the cell, cylindrical cell, prismatic cell, pole cell. We need to look at the geometry feature along with the metal properties, electrical properties, mechanical properties, thermal properties, all such things. Not only for the anode and cathode, I should design separator also properly. What about electrolyte? What is the role of electrolyte? In fact, we use liquid-based electrolyte for lithium-ion batteries. What is the property we should ensure for electrolyte? What is the role of electrolyte? As the lithium ions are moving back and forth. A lot of organic compound we use. We use as electrolyte. What property you should know for electrolyte? What does it conduct? What does it transport? Electrolyte, will you talk about electronic conductivity or ionic conductivity? Yeah. What is flowing in the SL circuit? What is flowing through this channel? For electrolyte, I have to ensure its very high ionic conductivity. Very high ionic conductivity. And it should be chemically stable. During charging, discharging, you try to experience very high I-square error loss, lot of heat dissipation. The electrolyte, if they undergo decomposition, what will happen? The electrolyte, you should ensure its very high ionic conductivity, thermal stability. What happens if the electrolyte decomposes? It undergoes degradation, what will happen? What is the role of electrolyte? It has to transport lithium back and forth. If you are not ensuring its very high ionic conductivity, if you don't ensure thermal stability, what will happen? It means that electrolyte also, there are thousands and thousands of electrolyte material. It is not that we use same kind of lithium-ion cell, same kind of electrolyte for all kinds of use case. Use case may be 2-wheeler, 3-wheeler, 4-wheeler, or stationary power storage. Each application is being unique. We have to choose appropriate material, appropriate design actually. Electrolyte, you have to ensure thermal stability also. Due to short circuiting, suddenly temperature rises to 200. All organic low melting point actually. They may vaporize, what will happen? If they vaporize, what will happen to the cell performance? We talk about cell venting out, suddenly gases are releasing, suddenly bursting out blast. So I need to ensure proper stability of the electrolyte, thermal stability, chemical stability. Above all, it should be highly conducting, ionic conductivity. What will happen to ionic conductivity with respect to temperature? Ionic conductivity with respect to temperature. We can tolerate up to 50 lithium-ion cells from ambient temperature to 50. What will happen to ionic conductivity with respect to temperature? Ionic conductivity with respect to temperature. You know, electric conductivity with respect to temperature. Ionic conductivity with respect to temperature, what will happen? What will happen to ionic conductivity? Compared to ambient temperature, if temperature goes to 50, what will happen to ionic conductivity? It will increase or it will reduce? Ionic conductivity will increase or reduce? Ionic conductivity will increase with increase in temperature. Unlike in electric conductivity, it will reduce with increase in temperature. Reason being, the ion can move much higher speed with increase in temperature. But again, we cannot increase to 150, 200 plus. The electrolyte will decompose actually. Okay, I'm just trying to highlight
anode property, cathode property, overall design, and the separator also. And separator also I mentioned about it should not be conducting, electrically conducting. We should ensure complete insulation. Dielectric property of separator actually. What thickness I have to choose, at what rate iron can move back and forth. Above all, appropriate electric should be chosen. Again, you see here, what is the comparison here? What I have here? Lithium ion. I all the time talk about cathode variety of materials. What do you have here? First one, second one, third one, fourth one, fifth one, sixth one. What do you have? Nominal voltage, cycles. What do you mean by cycle? Charging, discharging one cycle actually. And again, charging and discharging. You heard about C rate, 1 C rate, 2 C rate, 3 C rate, 0.5 C rate. What C rate I mean? When I say 1 C rate, capacity battery pack is 50 kilowatt. What does it mean? C rate, it refers to at what rate you are charging and discharging. Obviously, when you move towards 2 C rate, 3 C rate, at very high charging, I square R loss, we cannot escape actually. Okay, I already talked about type 1, level 1 charger, level 2 charger, level 3 charger. If you go for level 3 charger, quick charging. I have to look at what type of design I used it, what type of metal I have chosen. Can it sustain quick charging? We have to look at from all angles actually. Now you look at unique feature all the time. Why do you have thousands of lithium ion cell chemistry? Again, I want to highlight it's not one size fit for all. Each application is unique. Each design is unique. I cannot use particular design for any applications actually. I'm just trying to highlight different cathode material. What is the typical unique features? You tell me which cell you will go for. Looking at the typical nominal voltage alone, which one is more preferred actually? Hope you are able to see this slide. I'm just comparing among different cathode material their performance actually. Looking at this extreme left side column, which you did not just looking at the nominal voltage alone. When it's nominal voltage, I just talk about how much voltage you can expect from the cell actually. You are assembling cells, So which cell, which configuration you will go for? I put as red color, red color, red color. What is the unique advantage you have? You have here also here. Which one you will go for? You have cycle life. What is typical charging current rate? What rate? C rate you can use. Discharge current rate. And then thermal runaway. What the temperature is you can expect for each type of cathode when you use actually. And then you have typical packaging. I mentioned about different type of cell design, prismatic cell and things like that. What type of design we go for? What type of cell chemistry? Cathode material actually. And final, look at the extreme left, look at the nominal voltage, look at the comments. Which one you prefer? Why I mentioned about red line and black line? I just request you to go through it. Which one you go for actually?
First one.
Yeah. What is that?
Lithium.
Hope you are able to see. In cathode itself, we have variety of material. I need to look at the performance. That's why I mentioned when you go for buying new battery, it may be cheaper. I have to look at the specification. All the time we are after only cheap cost, cheap cost. At what cost actually? Now you should not look at blindly it is being cheaper. We have to look at the technical features actually. Now when you buy new equipment, we have to look at technical specifications actually. Okay, we have to look at the technical specification, not just looking at cost alone, price alone actually. So looking at the typical, at what C rate they can perform much better, looking at this beginning with their nominal capacity actually, nominal voltage actually. Again temperature rise also, depending upon being used for very low C rate and very high C rate actually. Okay, high specific energy, very low self-discharge rate for this lithium nickel manganese oxide. This I want to highlight the NMC we are using extensively. All light vehicles, 2-wheeler, 4-wheeler actually. That's what I highlighted in red color actually. Okay. Again looking at all the features actually. Cycle life, at what rate it can be charged, discharged, what could be temperature, typical thermal dynamic can occur. We will never allow battery to go to 210. It means what? Up to 210 your NMC can sustain. But with the proper sensing of the battery pack through BMS, we never allow the battery to go to very high temperature. Above all, we have taken care of proper cooling solution. Right now we use air-based cooling, active cooling and passive cooling. Now people are moving towards immersion cooling, and if you are aware, we talk about phase change material. Depending upon internal temperature battery pack, I call it a system, your passive material will come into picture. They absorb the heat the moment temperature is beyond 50 degrees. This is called passive cooling by using phase change material. Phase change material loss should not undergo decomposition. You should be able to take the heat and it can give away actually. The moment if it goes sub zero, the metal undergo transformation.
These are all phase-change materials actually. So I'm just talking about cooling solution. It's not only purely the role of chemistry. I'm trying to highlight expertise coming from different disciplines to ensure that battery pack can perform. Okay. Even aggressive conditions, battery pack should be able to perform much better. Accounting for having already developed the cells, I need to come to the role of both electrical and mechanical to ensure that battery pack is able to deliver the record life. Typical life of the battery, you know how much? You know what? Total battery pack. What typical life of the battery pack would you buy? Yeah, how many years? Normally they say 8 to 10 years. Now people are working towards to increase their life further actually. Okay. It is possible to increase the life also further. Again, I mentioned about choosing new cell chemistry and then playing with the design. So I just mentioned about, just to put it broadly, all the cathode material I mentioned about transition metal oxide, wherein we are inserting the lithium during charging and discharging. Variety of cathode material. And what about anode material you see here? I mentioned about graphite. Now people are slowly moving towards silicon also. So what is the advantage you have? Just compare graphite. I mentioned about people are slowly moving towards silicon. Silicon also they look at raw material. For example, simple rice husk possible to extract silicon economically. Slowly people are moving towards silicon. What is the advantage you have? Just compare these two. What is it? You assemble 1000 cells by using silicon as anode compared to graphite as anode. Number of cells being used to achieve record capacity can reduce drastically if they go for using silicon. Again, we are comparing among different anode materials: silicon, graphite, lithium, titanate. They are all anode materials. Look at their once again nominal voltage. What is the specific energy you can get per kg basis? Now, which one you will choose? Comparing among specific energy, capacity, cycle life, and then commercial velocity. Which one you will use? Which one you will use? Which anode you will use? Again, of course, we have to look at cost also, but if you are looking at this table, which one you will go for using? Right now, you are using graphite. Which other anode you will use? Yeah. Which one will you use? Yeah. High energy density, capacity depend also much. Capacity is good, no? Greater than 1000. Now, people are slowly moving to a second. Above all, I already mentioned, people are also talking about anode-free lithium-ion battery. When I say anode-free, then what about the role of anode? Your copper current collector itself is going to act as anode. When they undergo reaction back and forth, there is going to be lithium deposition at the copper current collector. That is going to act as anode. When I say about anode-free lithium-ion battery, it doesn't mean that there is no role of anode. At the copper current collector, during reaction, lithium is going to deposit. That is going to act as anode for the reaction to undergo back and forth. Okay, so people talk about anode-free lithium-ion batteries also. And again, see here, light vehicle. We have here, you can see what is typical light vehicle. What help to buy total weight of the vehicle actually. You just see here what features you have. What is the model you have? You just look at. Yeah. What are you able to see? The energy stored, battery pack, two-wheeler. What is that slide talks about? I have given complete picture. So I can talk about theory, all technical specification. At the end of the day, I have to see who is using, what advantage you have. You just look at here. What extreme right you have. Cost of the vehicle. Okay. You have battery life. And we have here charging time. And then we have here battery pack, number of batteries per two-wheeler, how many we use here. And then we have typical how much energy we can store. And extreme left, once again here, what are these we have? You look at my under. I have given complete information for different manufacturers actually. Okay. This is very informative for you to look at what is what actually. Their life. Ultimately, I'm looking at the typical battery capacity, what the life it can give. Okay. Comparing among different LV is light vehicle battery. Light vehicle, you should know what is typical battery capacity from manufacturer to manufacturer. So this is just information. Informative. And again, these for heavy vehicle. Look at once again Ashok Leyland, Tata, JBM, and here another Opera, Volvo Group. Again, look at the model name. What is typical weight? Head weight means overall weight of the vehicle. And then we see what is the energy stored for each type of model. I'm just talking about previous slide was two-wheeler. This is for four-wheeler actually. It's very informative. I'll just move quickly. Likewise, we talk about truck also.
Tata Motors, Ashok Leyland, once again Tata Motors, different models. Again, looking at the overall weight of the vehicle, battery capacity. Ultimately, we should know battery capacity, how long vehicle can go on the road. I should know what the capacity of the battery, no? How many miles I can go to one go for one charging actually. Again, this for heavy vehicle. Previously for light vehicle. Prior to that, I showed two-wheeler. Here, heavy vehicle and talk about light vehicle and heavy vehicle also. Different type of model, their capacity and so on. I'm just interested to know the battery capacity. And now I'm going to discuss about the SOC estimation also. Here, this 1 second per track. Yeah. 1 second, we talk about company model, Ashok Leyland, the typical battery capacity, type of battery, what type of battery they say use. Once again, lithium-ion battery, NMC battery they use for heavy vehicle, Ashok Leyland. Yeah. So now coming to battery modeling. So far I think it's clear to you know what factors I need to consider. Properties are important, particle, nanomaterial, electrolyte, separator, and so on. Now coming to I want to estimate SOC or capacitive battery pack. What is the approach we use? We have different type of why electrochemical. In fact, it's also possible to electrical modeling. When I say electrical modeling, before I discuss electrochemical modeling, in the electrical modeling, what we try to do, we have anode, cathode, electrolyte, separator. The battery response is mimicked in terms of equivalent electrical circuit elements consisting of conductor, resistor, capacitor, and inductor. We are translating the battery response in terms of whether they are conducting or resisting. We try to mimic the response of the cell or battery pack in terms of equivalent electrical circuit elements. Depending upon how they are being arranged, the series, parallel series configuration, by constructing equivalent electrical circuit model for a given input current, what is the output voltage you are going to get from the cell? We can model. You know about Ohm's law. You know about Thevenin's theorem, Norton theorem. What for you are using Thevenin's theorem, Norton theorem? You have already done circuit theory course. So electrical modeling also for the battery pack, we can estimate SOC. Compared to electrochemical modeling, they are approximate. In the electrochemical, because we are exploiting electrochemical reactions, they are much more fundamental. You cannot say that I am with the electrical background, I should not care about electrochemical modeling. Ultimately, if you want to improve even 1% improvement of the battery, I need to know how the reaction occurs actually. What speed it can occur. Can I do quick charging? Cathode, can it afford to undergo quick charging? I need to come to electrochemistry. Being an electrical person also, I should know fundamentally what drives the reaction when you do quick charging, quick discharging action. Having understood fundamental electrochemistry, later on you can go for using electrical modeling. SOC estimation, battery capacity can be estimated just by using electrical modeling. There are software available, but it will approximate actually. By going to the electrochemistry principle, possible for it to establish the previous estimation of SOC actually. Okay, having discussed about all capacity, we need to know how to model set of charge or capacitive battery pack by going to electrochemical modeling. The variety of modeling we have, microscale model, single particle model. I am going to discuss about is less computationally intensive pseudo two-dimensional model, P2D model. Pseudo two-dimensional model. This is the model we use to estimate SOC of the battery pack. But when we go through this first and second, they are much more complex. Much more complex in the sense at the battery pack level, macro level, this is going to be much more rigorous, complex. Computationally, they are very much intensive. Looking at computation time taken, we always opt for going through this pseudo two-dimensional model. If you ask me what this modeling does, I'm not going to too much abstract mathematics. This pseudo two-dimensional model, simply to put it in simple terms, what is the driving force required for the reaction to undergo back and forth? If you have energy, if you want to move on the road, if I run fast, what speed I can run? I should know how much potential energy I have. Simply the pseudo two-dimensional model accounts for when you want to drive the reaction, having already known the properties of the material being used for cathode and anode, whether it can trigger the reaction or not. This we call from thermodynamic perspective, what is the driving force required? Like how much energy I need to have if you want to run 10 km per hour. Like that, for the reaction to undergo record speed, we talk about what is the potential you require, driving force you require. That comes from thermodynamics. And what speed I can move, at what rate I can move, this we call kinetics. This we call kinetics means rate. Rate at which it can. I talked about lithium ions are moving back and forth. At what speed? This we call diffusivity. At what speed they can move.
I'm just talking about what fundamental principles are required to develop a mathematical model connecting input to the output. What input you are giving to the battery, what is output you are getting, they are being interconnected to each other. Through the pseudo two-dimensional model, by bringing electrochemical principles, wherein we consider properties of cathode material, anode material, again from thermodynamics and kinetic perspective, I know how much potential or driving force is required to drive the reaction. At what speed this has to undergo, I'll talk about lithium ion movement. At what speed, that's why I'm talking about quick charging, quick discharge action. It all finally boils down to internally how the lithium ions are moving back and forth, what speed they can move, and how much energy it has got. All things are coming under thermodynamics and kinetics. The thermodynamic properties, kinetic properties, they're all being used to do simulation for SOC action, to do simulation for startup charge for the battery pack. This I talk about pseudo two-dimensional model, which accounts for all electrochemical principles in terms of both thermodynamics and kinetics. Both are complex, they are much more useful, computers less intensive actually. Yeah. Again, you see here, I just forget about this micro model, the previous thing. I just directly come to pseudo 2D model. Yeah. I just mentioned about thermodynamic principles and kinetic principles. What is that internally we have? Just talk about here. I mentioned about lithium ion movements, no? This basically, see, I talked about lithium is being lightest. Being lightest, being atomic is very less compared to other metal. They can, very low mass actually. They can easily move. What about electron mass? What is electron mass? Electron mass? Negligible mass, no? But lithium ions being lightest metal, they can move very fast. Okay, dust particle being lightest, they can float in the air, you know. Lithium is being lightest, they can move very fast. But what speed they move back and forth, mathematically how do you express? This we should know this we call fixed law of diffusion. I'm talking about reaction at what speed they undergo, back and forth. We are giving input, what is output you are going to get, how they are connected to each other, that we are expressing mathematically. This we call governing equation. Just to introduce the term called. When you want to do battery modeling, we are just translating your physical information in terms of mathematical abstract term. We are connecting input to the output. Rather, we are connecting it to independent variable to the dependent variable. If you have only one independent variable, mathematically put it we call ordinary differential equation. I'm just introducing layman language actually. If you have more than one independent variable, take the battery as a system. You take rectangular box. The spatial, you look at dimension of the battery being prismatic, symmetrical cell. Independent variables are space, time. In a given space, if you take another dimension, rectangular space, how much mass of the material can be put in actually? At what time frame they can move back and forth? So this is called spatial and temporal evolution of your battery pack instance of electrode material, being anode and cathode, electrode dimension, the whole dimension, how the ion can move back and forth spatially as well as a function of time. So spatio-temporal evolution, or rather diffusion of the ions moving back and forth, that is expressed through fixed law of diffusion. Fixed law of diffusion. You know about osmosis process? Osmosis, what is osmosis process? You remove the impurity from the water purification. You know about reverse osmosis. Okay. To do reverse osmosis, to purify the water, what do you require? What is osmosis? You already know. I'm just trying to connect with the layman term. It's not a big equation. I'm just expressing mathematically. When I say dose by 2, you know about from higher concentration goes to higher concentration, you know osmosis. Same thing, the diffusion process, I'm expressing it mathematically. As a function of time, as a function of spatially, we have particular dimension. Okay, how they move back and forth actually. I'm just referring to, just take lithium is moving. C is nothing but concentration. Okay, I'm just putting it in simple term what the equation talks about. In fact, you know about whether you are an electrical person, mechanical person, when you do modeling, what I do to conserve is the energy conservation, mass conservation, momentum conservation. Can you escape law of conservation of energy? First of thermodynamics. Whether you're an electrical person, you take care of charge balance. I talk about Thevenin and Norton there. What do you account for? Ultimately, I have to talk about charge conservation. In fact, if you ask me the first time what does it take care, when I mentioned about all the time lithium is diffusing, I want to know at what speed it is moving, where it is entering, where it is coming out, doing the process of movement in the cell, is it getting accumulated or is coming freely? Whatever is entering, if it comes out freely without any interruption, that we call steady state diffusion. You all know the term difference between steady state and unsteady state actually. Since it is unsteady state diffusion of lithium ion, when they move from anode to cathode, we try to bring unsteady state diffusion of ions through the compartment of the cell. We bring this fixed angle of diffusion. This first equation accounts for mass conservation. And again, the ions are carrying what? When they carry the mass, I bring diffusion. Looking at their atomic radius, I know at what speed they move. I account for mass conservation. And what charge it carries? What will I have to bring? This takes care of mass conservation using fixed angle of diffusion, unsteady distribution. This takes care of lithium ion is carrying charge. I should account for what charge is coming in, what is coming out actually. I should take care of charge conservation, mass conservation and charge conservation. So basically I am building a mathematical model to estimate setup charge by the battery pack, looking at fundamental principle from, I mentioned about thermodynamic principles, what is driving force required to drive the reaction, and then what rate it can move. It is governed by this fixed law of diffusion. It accounts for mass conservation, charge conservation taken care through Ohm's law. And ultimately by combining all, this is the most celebrated equation called Water-Balmer equation. By combining all of them, it is trying to relate between, you can see here, is basically our current density for the battery. And here internally we have over voltage. Okay, over voltage is nothing but the voltage difference between actual value and theoretical value actually. Because of I square R loss, you don't need to get actual voltage actually. You don't need to get theoretical voltage actually. That we call over voltage. I am trying to refer, due to your resistance or I square R loss, the eta is called over voltage. I am trying to refer the term called over voltage is nothing but equilibrium value and the actual value. The difference we call over voltage actually. So we are trying to relate fundamentally combining all these charge conservation. Charge conservation comes from Ohm's law, mass conservation comes from fixed angle of diffusion. By combining all of them, finally I need to use this Water-Balmer equation. It connects between current density and over voltage. Internally this term takes care for anodic part, second part takes the cathodic part. Internally we have all electrochemical parameters actually. It means that what? We are able to relate why this is so important, electrochemical modeling. The electrochemical modeling precisely accounts for current voltage relationship for the cell with all the electrochemical parameters in terms of their reaction rate. Time and again I am relating, to put it in simple term, current voltage at the cell is being intimately connected to reaction rate constant. To put it in simple term, this first term and second term precisely accounts for reaction rate. The reaction rate is directly, if you say very high current, maximum voltage, that is connected to reaction rate constant. You already have a high school chemistry. Reaction rate constant. Reaction rate constant is intimately related to your current density and over voltage. This reaction is being electrochemical reactions. Since they carry the charge, okay, we try to relate between current density and over voltage along with the reaction rate constant. This is for first part is for anodic part, second part is the cathodic part. So Water-Balmer equation, having known the reaction rate constant, having known the what type of metal I used, I should be able to establish current voltage relationship for the cell actually. The reaction rate constant is known, you can determine current versus voltage. If current versus voltage is known, I can determine what the reaction rate constant. Can you improve the rate constant further? It's possible to manipulate all the parameters. That's why we do simulation now, we try to give inputs. For all the metals are known, we say parametric study. We can alter the parameter, we are going to see the effect of it, how it is going to influence current versus voltage for the cell actually. So this fundamentally is a electrochemical model accounts for connecting reaction rate constant with J is current density and eta is over voltage actually. Since we have both anode and cathode, both part we are combining actually. Okay. Simply we are trying to solve Water-Balmer equation to determine current versus voltage at the cell. Are you able to get what I am saying? Accounting for charge conservation, mass conservation, you consider battery pack as a system. What goes in, what comes out. And within the cell, we have anode, cathode, electrolyte, separator. Account for properties of all the individual part, being active part, passive part. Everything goes into the model. But I am going to show having this particular model. We can import this model from software called ComSol software. It's a multi-physics software wherein we have exclusive model for battery pack modeling actually. This equation you need to solve. You don't need to do rigorous coding. It is like using your MS window actually. You can choose the model. You can give the input property for the lithium cell. Everything is user driven. Very good graphical user interface. Okay, you don't need to do rigorous coding. Having understood fundamentals, you can pick up the appropriate material with the appropriate properties and then
You can even design the particular cell also being prismatic cylindrical cell. The CAD models are there. That's all inbuilt within the console itself actually. So these are fundamental equations we use to solve. Okay. And again, energy conservation. In fact, I talked about the ice core loss. Batteries being charged quickly or slowly, like a discharge also. There is always a ice core heat is spent. Again, I have to do energy balance actually. How much heat is being generated? How much is being dissipated to the outside? Again, it is connected to the cooling source what they provided. With the cooling, without cooling. So I bring along with the Butterworth equation, I try to do energy balance. What the heat is being released, how much heat is going to be released when the battery is undergoing charging and discharging, whether I cool the battery effectively or not. For that, I will build a thermodynamic model also I bring. Okay. And again, it is connecting over voltage with the current. All the terms are here. All the terms, all these terms should be known. What property we should know. Everything is given in the table here. I'll use all this. Yeah. And again, the battery also I talk about aging. Like I mentioned, the fresh battery. What is the OCV? If it is already used for 5 years, again the OCV will reduce. See, aging phenomena also we can simulate. How do you simulate aging? Let us say you are buying the battery. How do you know it's a fresh battery or already used battery? What do you do? Let us say I have done test for the battery for 1000 cycles. I can predict what is the life left for the battery through modeling. Having known the past and present, I can predict the future also. How do you know fresh battery or old battery? Just by measuring. Just by measuring what? Just by measuring OCV, you will know. OCV value also it will diminish as a function of time. If it is already used for 2 battery, you will not get the same voltage like what you got at the beginning. New fresh battery actually. So aging phenomena, when I say, you try to see their properties. Property will deteriorate. Ionic conductivity of the electrolyte will diminish actually. People use sensor also. Just by measuring impedance. Just by measuring impedance of the battery pack, possible for it to connect it to SOC. Possible for it to connect it to the aging, at what is their aging. The ionic conductivity, electrical conductivity, thermal stability, they are all going to degrade as a function of time. Okay, aging phenomena can be estimated by just by sensing their current voltage and temperature over a period of time actually. We can use sensor non-destructively. Okay. And again, during the course of estimating the parameter, we can do optimization also. So optimization it enables you to do partial estimation of the SOC actually. This I can discuss in detail. And again, this of course BMS I talked about like current sensor, voltage sensor, temperature sensor. This I will not go into just to show you. BMS is equally important to see that your battery health is being taken care when it is being charged as well as discharged. And here you see state of charge estimation. How do you estimate? There are different techniques. We use Coulomb counting technique. Coulomb counting technique, battery is being connected to external load. You continuously measure the current. I'm going to show the formula also. How do you estimate SO? It's simple by using current measurement. This we call Coulomb counting method. We continuously monitor the current as a function of time. I will show the formula also what you use to estimate the SOC for a given battery pack. And the electrochemical impedance spectroscopy also used to precisely estimate. And having measured current as a function of time, you know about Kalman filter. In signal processing, what is the role of Kalman filter? What is the role of Kalman filter? What does it do? It removes the noise, removes the error. You will be able to estimate precise SOC for the given battery pack. You are measuring the signal continuously, you remove the noise, like filtering. You will be able to estimate SOC more accurately based on Kalman filter technique. And again, we have optional voltage measurement also. In Coulomb counting technique also is routine procedure. We estimate the current as a function. We call ampere hour. Okay, I just directly go to current integration. You should know initial SOC. And this typical flowchart to show you how SOC is estimated through Coulomb counting. And this is the, you can see here SOC. The formula what you have written. I already showed Butterworth multiplication. Before that, I'm just building up what is SOC, what is the formula used. I mentioned about Coulomb counting. What is the formula you have here? Set of estimation, this is the formula. What do you have here? Q is nothing but rated capacity of the battery, ampere hour, and T0 is the initial charge of the battery, ampere hour, P0. And what you are trying to monitor continuously, the integral, what do you have? What is this? This is the current. Eta is the over voltage. Again, I want to refer the actual battery voltage, what you get is not going to be the theoretical value. What is the reason? What is the reason? What I mean by over voltage? What is over voltage? You never get the theoretical value, no? Why the value, actual value is being lesser than theoretical value, equilibrium value? Because resistance. resistance you can never escape. Coming from the electrolyte conduct resistance, the electrochemically we try to relate it to polarization. When the ions are moving back and forth, I talk about ionic conductivity. Ion may collide. That is connected to polarization. Ultimately, I am connected to resistance arising from electrolyte, separator, even container. Everything going to affect what voltage you are going to experience into the actual measurement. That's why we take the difference between actual value and unitary value that we call over voltage. We are trying to relate between over voltage and current density. Why all the time talk about current density, not current for the battery? The given dimension of the electrode, what is the current density? The amount of current flowing per unit area. Normal conducting wave we talk about current, we don't talk about current density. But the battery all the time we talk about current density, the amount of current flowing per unit area with respect to particular design for the cell. Is a rectangular cell or cylindrical cell. I already mentioned about spatial and temporal evolution. In a given space, how much mass of the active material I can put in actually. When I say active material, cathode material, non-material actually. So I should know how much current can flow per unit area. Spatially, I take rectangular sheet. Okay. How the ions are moving as a function of time and space area actually, depending upon how much material I have put into a particular space actually. That's why I talk about current density. The amount of current flowing per unit area. How thin the electrode? How thick the electrode? It matters. From geometrical perspective, I have to look at dimension of the electrode. How thick, how thin. Thicker the electrode, what will happen? Thinner the electrode, lithium can easily come and go. If thicker, it will take more time. The residence time for the ion to say the thicker, it will take more time before it comes out actually. So dimension is very critical. So you have here SOS estimation, Q0 already mentioned rated capacity, current, over voltage time, and again you see you are integrating from where to where, from starting to time. How much time you take for complete charging? The SOC can be estimated during charging also. At what rate you are achieving 100% SOC, and when you drain out also, depending upon at what rate you are draining out, I can estimate actually. At what rate you are draining out the battery to depth of discharge being 5%, 10%, and so on. And you will never drain out the battery to completely drained out. Will never go actually. And again, you do calibration also. I mentioned about common filtering. It's all signal processing. And again, cooling counting also, if we have some limitation, that's why we try to bring the common filtering to make it much more precise when you go for SOS estimation. Okay. Yeah. So once again, the setup charge, if you want to express this is the typical formula. Okay, formula we use. And again, you see initial charge of the battery, and again you see Q is nothing but quantity of the electricity. Okay, determined by the battery. I just already gave the formula. Cooling counting, we just try to measure the current as a function of time. I already saw the formula also. Once again, to reiterate what I mean by setup charge actually. You should know why should I care about Q0 if I ask you this formula. Hope you are getting. The purpose of this talk, I should know how to estimate SOC of the battery. So what is that you have? The formula here first. What is the first one? What is this Q0? What is Q0? What is Q? What is Q max? And here SOC, initial SOC of the battery. To use this formula, all the terms should be known to you. What is that? You have Q0. Why should I care about Q0? Battery method is already reached 100% depth of discharge. Before you go for charging, what is the initial condition of the battery? Is it completely drained out battery or a positive discharge battery? If it is fully charged battery, for all such cases, all the terms should be known to substitute to estimate what the SOC of the battery. We use mobile phone, we use it for 5 hours. I can know how much it is being already utilized, how much it has been drained out. I can determine the SOC of your mobile. It comes for 10 hours, used for 5 hours, what the SOC left actually. I need to consider what is the initial state, then go for necessary current or voltage to determine the SOC actually. I need to know in terms of percentage actually, in terms of percentage. In fact, the vehicle, you can indicate like a meter, SOC you can estimate 50%, 60% is utilized, how much is left actually. And state of health, state of charge I said, state of health, what do you have? Current capacity of ampere hour, day to original capacity. If you ask me what the difference between state of charge and state of health, state of health, as a function of time, when you use the battery for large number of cycles, we are looking at aging.
What is the current health of the battery? Fresh battery and old battery. Used battery. The SOH estimation, I should know SOC also. SOC should be known as a function of time. How many number of cycles I used it. If you account for that, I know setup health actually. Having known setup charge and setup health, I can determine capacity fade actually. You look at the formula capacity fade. At what rate I am undergoing aging. If I don't do any exercise, always sitting in front of computer, always being sluggish, I only use brain, what will happen? All your vital parameters, blood pressure, sugar, if you don't do any exercise, same thing for battery also. You are abusing the battery. Of course, your BMS will never allow you to go for overcharging, over discharging. Okay. So all such cases, I should know at what rate I am undergoing. That we call capacity failure. Again, connected to, we always talk about quick charging. Suddenly you are applying the brake, you did huge amount of power. That means it's called, you heard of a random load. It's called stochastic load. We are not uniformly discharging. Okay, this is called stochastic load, random load. Due to random load, what will happen? Battery will undergo quick aging. You are applying brake frequently. That won't affect the health of the battery pack. Okay, bus moving in the city and bus moving in the highway. Bus moving in the city, it undergoes very fast aging. But again, the city bus also, since you go on the road due to traffic, when you apply frequent braking, there is advantage for regenerative braking. You are able to recharge the battery when you apply the brake, regenerative braking actually. So I just introduced different terms: setup, charge, setup, health, capacity fade, power fade is also already given. Used capacity. I already mentioned about C rate, 1 C rate, 2 C rate, 3 C rate. If we want to know what is the rated when you buy the new battery, I should know at what rate it can work well. Can it afford to do quick charging when you go for 2 C rate, 3 C rate? Already technical specialist should do actually. Normally, we use 1 C rate, but during charging, if it is able to take care of 2 C charging, they design appropriately. Otherwise, it takes a few hours and so on. Normally, we take 2 or 3 hours. The battery pack is being less expensive, cheaper, but we cannot do a very quick charging actually. The way the battery pack has been designed actually. Okay, we use C rate during charging and discharging. Whether you use 1 C rate, 2 C rate, the C rate is going to affect your your SOC also. All the time I do quick charging, all the time I discharge the battery quickly. It's going to affect the current voltage performance of the cell or battery pack actually. That's why we express in terms of C rate. At the very low, in fact, we are talking about life of the battery. We always use only 0.7 C charging, discharging. Battery will come for longer time. At what rate you are charging or discharging, that is being expressed by using a term called C rate, rated capacity of the battery. Rated capacity means what? At what rate I am discharging? All 50 kilowatt per hour, or you getting to 1 hour, or you're going to take 10 hours to drain out the battery actually. Okay. Power is nothing but already current multiplied voltage. Okay. At the very high discharge current, what will happen to the voltage? You are trying to drop more current per unit time. What will happen to voltage? Voltage will drop actually. In fact, there is one law called Pickett's law. At the very high discharge rate, if I impose very high discharge current, voltage will diminish rapidly. Or SOS is going to diminish rapidly. Okay, you should know what C rate, at what rate you are draining out the battery, like a charging also. Everything connected to I square law. To put in simple term, I square R during charging and discharge. How you have designed, whatever material you have chosen. Ultimately, everything, to put it in simple terms, knowing properties of material, anode, cathode, electrolyte compartment, plus giving appropriate design to it, you are developing a product or component. I mentioned about what is the spacing you give from cell to cell and how do you interconnect them. Material plus design, you arrive at component device, whatever you want actually. Fundamentally, since I know properties of the material, I know the design, I couple them all, that's why we talk about mathematical model. Mathematical model to do simulation. What is simulation? It is nothing but virtual experiment. Virtual experiment. If you want to do actual experiment, I need equipment, I need raw material. But what is required in computer simulation? I need to know the physics of the process, go domain knowledge from electrical, mechanical, everything being put into mathematical form, connecting between dependent variable and independent variable, what are the influence variable. SOC, let us say, is a dependent variable. SOC dictated to be what are the factors? SOC, let us say SOC. I talked about Butterworth equation. We are relating between what to what? We are relating between over voltage and current density.
And to determine SOC, I am continuously monitoring current of the particular cell or battery pack for a period of time and use the formula to estimate. Having known the initial state of charge for the battery, as a function of time, when you continuously monitor current as a function of time, using the formula, I can determine what is SOC. Okay. Yeah. Again, software. In fact, I talked about all basics for the equations. Yeah. And again, to use the software, we can go for using COMSOL multiphysics software. And what are the you have to choose. In fact, the COMSOL software you can choose what specific lithium and cell chemistry you are going to choose. Everything can pick it up. Anode also you can choose. And the database is there. Like to do experiments, I need raw material, equipment. When you want to do simulation, what is required? You know fundamental principles govern the whole process. Plus all input database I should know. If I choose graphite as a anode, the property should be known. Database already available. You should know what is input, what is the output you are going to estimate actually. Output basically I want to determine SOC by knowing the current versus voltage characteristics actually. In fact, I just go back to 2 minutes here after some time. Yeah. The model also 1 second I go to yeah. Yeah. I mentioned about equation alone, no? Mass conservation, charge conservation. This I did not highlight. What is boundary condition? We always talk about initial condition, boundary condition. To put it layman term, battery pack is the closed system. What goes in, what comes out, what typical dimension that I refer actually. What does it mean? This means that when they say ions are moving back and forth, where it enters, where it comes out. It is like anode current it enters, it comes out at the cathode current current. For mass conservation, charge conservation, I need to know what the boundary condition. When I say boundary condition, it is not an open system now. Battery pack has got particular dimension. Where it comes in, where it comes out. During the post of when it comes out, the intermediate stages, is there going to be charge accumulation, mass accumulation, everything is being accounted. Can we impose these conditions? Yes, we are doing it in the closed system actually. This is what we talk about boundary condition also is case. Charge conservation also. Okay. When you want to solve the equation, it is not open. Okay. It is not, when I say open system, it is not both the mass and the energy exchange with the surroundings. Okay. It's only energy exchange between your battery pack and outside. When I say Eisenhower laws heat dissipation, I need to dissipate the heat from the battery pack to the outside. This is only an energy exchange. Mass is not being exchanged in the surroundings. Hope you are getting what I am saying. Having known the formulas, having known what is mass conservation, charge conservation, I should know what is the boundary condition you have to impose when you solve the equation. Through that COMSOL software, possible to include all such things when you want to solve the equations. In fact, all the typical parameters are required when you want to solve. Again, referring to anode, cathode, the thermal property, electrical properties. Okay, everything is being accounted. All these properties are available in the software database is available. There are input is required. And again, I can create this. You want to do simulation for SOC for the particular bag. I can choose cylindrical cell, assemble them. Through CAD software, I can develop. It's inbuilt software within the COMSOL itself. Now, you want to take 10 cell, being connected series parallel, you can create such geometry. So design is accounted. What type of design is used, whatever material is used, everything is there in that software itself. Now you can give us input. Yeah. Again, this also all type of input to the battery model parameters. Yeah. So this is typical input. Now, I already mentioned this. Through CAD model, you develop all the inputs for the material. It's all manipulable. Like you use MS-DOS. COMSOL software is very easy to use. Okay, it's basic numerical software. You can create geometry of the particular battery pack. You know what inputs are required. I already highlighted all the type about cathode properties, anode property, what the dimension. Okay, everything is input database available. Choose the model, choose the particular geometry of the particular battery pack. Through COMSOL, COMSOL. COMSOL is basically multiphysics software wherein we have exclusive module for battery pack simulations. Simulation is nothing but virtual experiment. I already know how the system it works. I try to represent the form of mathematical model. Mathematical model, I am connecting between input to the output. Okay. What I need to input to the output? For the given battery pack, let us say you are giving input being current. What is the output voltage I can get? And vice versa actually. And input and output they are being connected. To put it in simple terms, Butterworth equation, if you look at more deeply, it is nothing but partial differential equation. To solve it numerically, we are using COMSOL software. We cannot solve it manually. You won't get
accurate solution, we go for numerical software to solve it actually. So build 2D form, it is easily solved by manually. But such complexity, so many parameters are involved, you cannot solve analytically. This is called analytical method and numerical method. We solve these equations by using numerical method, by using software. That's why I mentioned about COMSOL software. So all the properties can be chosen, model can be chosen by applying upward boundary condition. In fact, what is the final ultimate going to get by doing simulation through COMSOL? What is Pascal? Can you see this? What difference between this? SOC versus? Yeah. Let's see. Look at my left figure and right figure. I'm just solving Butterworth equation. I'm giving input. I apply boundary condition. What the left side figure and right side figure? What is it I'm doing for the fact? What is it I'm trying to do? SOC versus charging time to achieve 100% SOC. How much time is required? Okay, for the particular lithium ion cell chemistry to reach 100% SOC. How much time does it take? Again, accounting for C rate of charging. Okay, accounting for C rate of charging, I can estimate how much time does it take to reach 100% actually. Total SOC 100%. This means that battery is totally charged when it reaches 100% actually. This is charging time. The SOC charging time. This is for SOC discharge time actually. Okay. Through COMSOL software, possible to get such figures actually. How much time does it take to reach 100% SOC? During charging, and when I say discharging, how fast you reach depth of discharge being 5% or even 0% and so on. Again, discuss what you see here. Cell potential versus time. I mentioned about at the very high C rate of charging, discharging. When you do very high discharge, C rate is being very high. What will happen to voltage? It will decrease. I cannot simulate from this curvature. I can simulate. Having known the input for all the materials, by using the equation, Butterworth equation, I possibly can also figures actually. How the cell potential is going to diminish as a function of time. Okay, that's why we talk about shallow discharge and slope discharge. Which one is better? Slope discharge and shallow discharge. Shallow discharge obviously good, but sometimes when you apply quick braking, you always go for very rapid discharging or charging. You should know what the discharge profile, shallow profile or slope profile. Depending upon that, your SOC is going to change as a function of time. All such things you can impose. Here you can see we are imposing different type of cells, cell 1, cell 2, cell 3, for different cell configuration. Even I can estimate, since it is coupled with thermodynamic model, I can see temperature rise also, being shallow discharge, slope discharge. Apart from determining SOC, I can determine what could be temperature rise. Along with it, if I have given proper cooling, I can always ensure temperature will never go beyond 50 degrees. All such things can be estimated a priori by using this software. Again, this typical cell configuration is simulated. 6 cells. What is typical configuration here? 6 series to parallel configuration. We simulated it. We have determined what the temperature is, what the SOC of the battery pack. This 1 second temperature rise also we estimated. What does it mean here? Hotspot. What does it mean? Different colors. What does it mean? I mentioned about load imbalance. Some location temperature rise. All such things can be. You can visualize color. What is temperature rise for the typical pack actually? So it comes out situation. Yeah. So just to conclude, to estimate state of charge or capacity of the battery pack, we can use electrochemical modeling, wherein we are simply solving Butterworth equation, which relates between current density versus core voltage for the battery pack. And that is being connected to your reaction rate constant. Ultimately, what dictates you are able to get quick power from the battery fundamentally boils down to the electrochemical reaction rate. At what speed reactions can undergo back and forth actually. And in future, I want to convey electric vehicle whenever you buy, your manufacturer who has supplied the battery pack, he will continuously monitor your battery pack health by putting sensor to your battery pack, which we call IoT. Your battery pack health will continuously go to your OEM, manufacturer. That means when to replace the battery, when to go for new battery, will be intimated automatically. Future is going to be autonomous vehicle. Okay, that's where people try to bring LiDAR. There is going to be zero accident. Take my word, actually. World is moving at a very rapid pace. Autonomous vehicle is going to be reality. Self-driving vehicle, simply sit in car, use the remote, it can take care of everything actually. These are two eyes, it has multiple eyes. Things will go never wrong. And with the AI tool, everything is going to be fast. Now people talk about artificial general intelligence. We use several AI tools. All the AI tools are interconnected. It can take quick decision. Taking the data to size of 10 power 50. Can you imagine? The data is growing to the level of 10 power 20, 10 power 50. All undo instance can be accounted precisely actually. Your AI tool can do everything. It is going to be super smart actually. Again, AI is not going to replace. It is going to be enabler for you to do the job 10x faster. When I say autonomous vehicle is going to be reality, we try to bring expertise from all field along with the AI tool. AI tool, all AI tool are interconnected. So it can make good decision. Nothing will go wrong actually. Autonomous vehicle actually. We sense when it moves on the road, depending on the traffic condition, everything is sensed continuously actually. Even traffic control through IoT domain is possible to see which road. Already of course we have which road to choose and so on. With the autonomous, with the lidar, going to be much faster in future actually. Artificial general intelligence is going to be overtake the human capacity. Artificial general intelligence. All AI tools are interconnected actually. In fact, AI tools, no, we have a software for specific domain. When all the domains are interconnected, nothing will go wrong. Such things are developed right now. Already use their developed technology, they will reach at the appropriate time. They also look for money business. You know about OpenAI? Some Adman, he says about AGI is going to be reality within 5 years down the line. So being in Triple E, I feel like, in fact, I already discussed with the HOD also, future is going to be electric vehicle. There is going to be huge demand for Triple E. People who are good at power electronics, along with it, you should be good at using software. I talked about SOC, what is the life left for the battery? Like I said, the OEM and the manufacturer are continuously monitoring your sensor. They're putting sensor, they're collecting data, current versus voltage curve, your impedance curve. The data with the domain, you should be able to assess what sense it makes. Simply knowing coding alone doesn't help. Domain knowledge plus software used in a particular field, that will make it become king actually. That you have to realize actually. Even I have discussed with HOD, 3rd, 4th year, you can develop a curriculum integrating your domain knowledge with machine learning and deep learning. Whole world talks about machine learning and deep learning. You go to ChatGPT, Gemini, Glade, you give any topic. You want to look at, I talked about lithium ion battery, you go for silicon based anode. You try to give business opportunities for silicon based lithium ion battery. It will give all information. No time actually. So information is available. AI tool is democratizing the available knowledge. You don't need to be an IIT. Being anywhere, you're having access to every damn thing in the world actually. And one more thing I want to highlight. Now the whole country is going for one nation, one subscription for all journals. Now currently in IIT, we are spending 20 crores per annum for journal and books. Now it is going to be democratized. The whole country, whether you are from college or NIT college, one subscription, one nation. Alright, who is making money? Foreign public, they are making money. Millions and millions of dollars. That is going to go away from 1st January actually. That means you are having access to all latest e-books at journals also. Thank you all, and if you have any queries, I will be happy to answer that.
Any queries, participants?
From students, I want to take some questions. One more thing, I already talked to HOD, but I am planning to arrange for a trip to our institute. We have a charging lab, battery lab, and we have got research park wherein we have SLUC Center for Battery and Electrical Vehicle actually. You can come and visit, you will be motivated. Okay?
We will plan, sir.
Yeah, definitely.
We will plan.
Yeah.
Sir, I have a doubt.
Yeah, please.
Yeah, future automatic self-driving car will come in future. But our transport minister Nitin told India will never allow self-driving car.
It will come. It's all politics business. Slowly with the time it will come. See, earlier we were talking about EV is not going to be a reality, but government is going to promote. The whole world is going towards looking at carbon footprint. A lot of ocean failure using carbon computers we are releasing more. Now we are forced to go through EV. With the time everything will happen. See, you see the gap between developed country and development. And we are growing at fast pace because of the available tools, internet, AI tool. We can learn fast actually. We are in the growth trajectory, nobody can stop. Autonomous vehicle is going to be reality with the time.
Sir, good morning, sir.
anode to cathode. By
During
relying-
discharge, anode will undergo oxidation, cathode will undergo reduction.
Yeah.
Exactly reverse when you do.
Yeah,
Yeah,
I have a
sorry.
question about that. Okay, what about the temperature difference between the terminals?
Temperature, whatever you try to experience, that depends upon I square R loss.
Okay.
I square R loss once again depends upon whether you do fast charging, quick discharging.
No, about
The resistance arising from the compartment dictated by at what rate you are charging and what rate you are discharging. It's connected to shear rate.
Okay.
Yeah,
What about
sure.
the temperature in anode terminal and cathode terminal? Will it be same or different, sir, during charging and discharging?
During charging, discharging, as long as you have taken care of appropriate cooling, during quick charging, quick discharging, it will never allow temperature to rise beyond 40 to 50 degrees.
No, my question is, will it be same in anode terminal if it is 40? We will experience the same temperature in cathode also.
We want to ensure uniform temperature throughout, the way it is being charged discharge. There will be minor difference, but the way it has been designed, it balances everything.
Okay, while we are going for a cooling mechanism,
Yeah.
the
To answer this question, as long as you have taken care of appropriate cooling, that's why in fact I did not discuss. We use cold plate.
Okay.
Cold plate, it goes through both anode and cathode. That's why you can ensure uniform temperature of the both cathode and anode also. We have say cooling channel.
yeah, if I'm
Cooling channel, the way it has been put into internally, that will take care of the temperature, uniformity of the both anode and cathode. Yeah.
will it make any difference? The flow, okay, during charging my
Even
flow
if it is little bit difference is there, the cooling solution will take care.
Okay.
You can say fast cooling, the rate at which air is flowing. That's why I mentioned about thermal management takes care. Somewhere there is imbalances and temps. That's why I mentioned about thermal management and power management. Thermal management will never allow uneven temperature distribution charge.
in our
Let us say anode temperature is higher than cathode.
Yeah.
Cooling solution will get triggered. It will say that it will never go beyond that, or it will try to maintain both. Like power balance, thermal balance also it will take care.
Okay.
Yeah.
Actually, we are trying to do some experimental setup.
Yeah.
In that setup, we measure.
Like I
the-
said, temperature is more at cathode. It's
Yeah.
possible to trigger air to flow more into that location.
Yeah, that is what.
Yeah, that's
my-
possible to. Yeah, that's possible to do.
We want to change the. It will make any difference, okay? If I make a flow from anode
Tell
to
me, yeah,
cathode-
if it will make difference in terms of at what rate ions can move,
Okay.
how much charge you're getting. It's going to influence definitely.
Okay.
Yeah,
Okay. Thank you.
definitely it is going to influence. Consequently, it is going to influence.
You were talking about the different types of hybrid, like electric vehicles.
Yeah.
In that, you were mentioning about the fuel cell.
Yeah.
Fuel cell vehicles.
Yeah.
So in foreign countries.
Fuel
many
cell,
of the-
what is that product? Fuel cell hydrogen action, usually water only.
Yeah.
In terms of environmental damage and all, fuel cell.
So in foreign and all. They
For
are
buses,
also-
heavy vehicle they're using. They do cost benefit analysis, life cycle assessment. Fuel cell, it makes sense for certain applications. Yeah.
So though the efficiency is between 20 to 30%, why they are preferring for heavy vehicles?
Fuel cell, na?
Yeah.
That's why I mentioned product is water.
Water.
Water, product is water. Product is water and you are not damaging the environment and things like
So
that.
even the cost is also higher, compared to other vehicles.
Yeah. And fuel cell also, when they do life cycle assessment, for heavy vehicle application, it makes much more sense compared to using battery operated vehicle. It's application specific. We prefer in certain cases fuel cell as compared to battery operated vehicle. Fuel cell actually. Yeah.
What about the future of fuel cell in India?
India for buses it may come, but lithium ion already is available here, no? Throwaway prices. We will continue to use lithium ion. We will never go for fuel cell. There is another parallel thought. Future is going to be hydrogen economy. Like in our IC engine, no, you have petrol. You simply fill with the gas actually, hydrogen gas actually. Again, storage is the issue, but in future they say that is also going to be another one. Now already battery pack has been matured, no, technology. Of course, it's getting refined further. After 15-20 years, they say hydrogen economy also will come into picture. Thank you. Any more questions? So if you want to know further, you are most welcome to interact with me through email. My already this PPT is available here. Okay. So students can visit, even faculty also, they can come and visit our department. For information, we are offering next year onwards a 2-year MTech program in electric vehicle. If you are taking GATE exam, you can come through GATE. If you qualify GATE, you can apply for a 2-year MTech program in electric vehicle. Otherwise, already we are offering online 6 months program, certificate course on electric vehicle from our department. Plus, additionally, we started offering web enabled MTech for industry proposal. Already electric vehicle program there is, already we started offering. And in our department, engineering design department, I am taking care of a battery pack engineering lab. We have a charging lab, motors lab. We have all verticals. If you want to know complete picture about electric vehicle. Okay, I will arrange through your department, Jyoti. You can come and visit our lab or department. EV is going to be future. Again, I want to highlight electric vehicle two-wheeler sales is every year increasing by 10 to 15%. Future is going to be EV and your record electrical percentage. Okay.
Thank you very much, sir.
Yeah.
We had a very good session on battery management systems, starting from fundamentals such as types of battery, their characteristics, to detailed information on battery pack modeling, governing equations, and boundary conditions, BMS stage estimations with all the formulas. We also had some insights on console software.
Thank you.
I hope the session will be very useful for research scholars who work on battery management systems. Thank you very much, sir.
Thank you all once again.
I now request our HOD, Dr. S. Sendra Kumar sir, to honor our guests with certificate of appreciation and a memento.
Yes. Thank you, sir. Thank you. Once again, thank you all for all the students and faculty for listening to my lectures. Thank you so much.
Dear participants, we'll be having